So here is, I guess, chapter 11 homework, or chapter 11 homework. For problem number one, we have motion of a particle defined by a relation given to us. So basically, and then what we're trying to find or determine is the time, the position, and the velocity when the acceleration is equal to zero. So we need to take this equation here and take the derivative essentially twice, but take the derivative of it to find the velocity, and we do that with respect, we do dx with respect to dt, and so that's very, very simple. We get 24t cubed minus 6t squared minus 24t plus 3, and then we just take the derivative of that again, and which is dv over dt, and you get 72 times t squared minus 12t minus 24, and then going to actually laser pointer. So that is what we have there. And then we're looking for a equals 0. And what we just do there, we can break it down into components. I know I do that a little weird, but that's just how I was taught in freshman, sophomore year, and it works. And then we get that a is equal to 0 when t equals 2/3 or minus 1/2 seconds. And the minus 1/2 doesn't matter, so we can throw that out. So that at t equals 2/3, I just plug everything in. We find the velocity is negative 8.56 meters per second, and its position is 0.259 meters. So very, very simple first problem. And then move on to problem number 2. It's about a projectile entering a medium at x equals 0, initial velocity of 900 feet per second, and it travels 4 inches before stopping. Here we have our defined v, and for part A, we're looking for the initial acceleration of the projectile. So we take our initial equation that is given to us, and we know that the final v is equal to 0. Here we have that there, and so we know that the initial, we know that if it has traveled 4 inches, or we know we can find the k of the I guess resistance medium by taking it the initial velocity and dividing it by the distance traveled, and that gives us a k of 2,700 per second. Yes. So then we can find our acceleration from that, which is equal to dv over dt. And we know that v is equal to v of 0 minus kx and such. So I believe, so we know v0 is constant, and then minus kx. One second. Oh, sorry, my bad here. So we have, just going back over the problems, minus kx, and then it is the same as minus k d to the x over dt, and we know that dx over dt is equal to v, and so we get a equals negative kv, or negative k times velocity, so that's where we get for acceleration. At t equals 0, we just plug everything in, and we get minus 2.43 times 10 to the 6 feet per second squared. And then that is for part A, because that is the initial acceleration. And then for part B, we are looking for the time required, and we know dx over dt is equal to v, so we can take the integral of both sides and manipulate it a bit, and we know that v has components of x in there, so we put that over on the x side, and which is v0 minus kx equals t, or dt, and we're looking from 0 to x and 0 to t. So we get t, and then, I mean, this is fairly simple, but you can did a u substitution over here. You get t is equal to minus 1 over k times, or then the integral of 0 to x of du over u, and then this is where I sub the u value back in, because I guess 0 to x is not, oh gosh, I just didn't transform the u part. And so once we sub everything back in, finish up taking the integral, this is what we end up with, using a few basic, I guess, laws, or just how natural logs operate. Take the minus, make that a positive, and then leads to that guy over there. And then it's just plug and chug. We know that we make it 3.9 inches, which everything here is in feet, and so we just divide everything by 12. So 3.9 divided by 12 when we're plugging in, so you have to be careful. And after plugging in, we get our t is equal to 1.366 times 10 to the negative 3 seconds. And then here we have those balls dropped from a boat, so it strikes the surface. Initial velocity 16.5 feet per second. We have our acceleration equation, and we know it takes 3 seconds to reach the bottom. So we know that acceleration is equal to dv over dt, and since we have an acceleration part already, or since we have that already, we can do dv over dt is equal to 10 minus 0.8 v, and since this has v in it, put it under. It's very similar to the last problem. U substitution, we're going to end up with a natural log at some point. It's equal to t, and then we had negative 5/4 natural log of u, plug u in. U is equal to 10 minus 0.8 v. So then we do it from v to v0, or v0 to v, however you want to word that. Continue on with taking the integral, and then we end up here, and we get a time equation, and this, we can manipulate this to be able to give us the velocity up there, so we have to do a little bit of algebra, but give us a velocity at any given time. And so here, this part is all just manipulating, and then here's where we actually are reaching our final steps. Here's where we reach our final velocity equation. V equals 12.5 plus 4 e to the negative 4/5 t. And we plug in 3 seconds, and we get 12.86 feet per second. So we can tell that the water is slowing the ball down. And then, we are also able to, we have to continue that. That is just for part B, which was easier to solve, so that's why I did it first. And this is for part A. So since we have the velocity equation, we know if we take the integral of it, or that the velocity equation is the derivative of the position function. So if we take the integral of the velocity, we end up with the position function. And so this is just fairly basic calculus. Go from 0 to x, figure out the x position, and from 0 to t, through a bit of calculus, you'll see, or integration over there. We just keep it going, and +5, we end up with a position function. And since we know it takes 3 seconds to go down, it is 42.05 feet deep. And then I did a very bad job about dividing these. But we have the speed of a jogger defined by a velocity equation there. We have miles per hour in miles. We also, eventually down the road, we want to do it in feet per second squared. So we'll do some conversions later on. And so initially we are looking for the distance that the jogger has run in 1 hour. So we need to create a position function similar to the end of the last question. Here's our velocity function. This one took me a bit of time to integrate correctly, but eventually we got there. But again, once you divvy everything up, 7.5 could have been here or at the bottom there. Didn't really matter. It's a constant. Again, use the U sub, and then integration. Then we kind of go back, or I re-integrate everything. I'm not sure if that was the easiest course of action or not. And then we're just going down, manipulating to be able to get x on x alone, so that we can just sub in, we can put in our t value, which is 1, and we can get a distance from it. And we get that is 7.15 miles. And for part B, we're looking for jogger's acceleration. At some point, we're going to have to do, at some point, we're going to have to do conversion again to get to feet per second. You can see that here, point that out later. But we know that acceleration is equal to the velocity equation, or the derivative of the velocity equation. But we also have x in there as well in the equation. We don't have t, but we do know that dx over dt is equal to v, and so we can take the derivative of v with respect to x, and that will balance it out. Right. And so here we have v, and then we take the derivative of this equation and then multiply it all together. So here's the derivative of v, and this is what we get for our acceleration equation. And then we plug in a at t equals 0. We immediately get this value, but this is in miles per hour squared. We need feet per second squared. So this is where we do our conversion. And we get that a at t equals 0 is negative 2.75 by 10 to the negative 4th feet per second squared, which doesn't seem that bad. And then we just need to find the time it takes for the jogger to reach 6 miles. We have a good milestone here, knowing it takes an hour to go a bit over 7 miles, so it should be under 1 hour. And then I believe I took one of our old equations from over here and sent that over here, and divided 0.21, did some adjustments, plug in x equals 6, and we get t equals 0.832 hours. Question number 5. we are looking for the acceleration due to gravity of a particle falling towards the Earth. We're given that equation here. G is a constant, and I believe big R is a constant as well, so it's all constants up top. R is the distance away from Earth, I believe. And so we are looking for the escape velocity. We're also given hints here. That means that this will help with our integration later on. And when launching from Earth, we know that it starts here and goes outward. So we know our starting value is going to be R, and we know at some point we just needed to leave the atmosphere. We don't need it enough to go on for forever. So at some point we have V equal, or at some point out here we have V equals 0. So we're given an acceleration equation or function, and we know it is equal to dv over dt, which is then, we don't really have an equation of velocity or an acceleration equation with dt, but we know dr over dt is equal to v, and then we have dv over dr. We have dv over, you want to take the derivative of v with respect to dr, and so to get acceleration as well and multiply, but similar to the last question, but opposite. So this is where things start to happen. You pit those two against each other. We had v dv, and show that here, and then move dr over to over there, as you can see here. Take the integrals of both, and then we end up with these equations here. They're kind of canceling each other out. We had escape velocity squared is equal to 2 times gravity times the radius of the Earth. That's just our final escape velocity equation. And once you plug in these three are constants, and so our final or escape velocity is 36,695.1 feet per second. It's also important to note making sure we're using the right gravity, which is 32.2 feet per second squared. That's just a unit check to make sure it checks out. Then we have question number 6. We're doing a weight handle thing. So it's important to note the entire cable or length of the cable stays the same no matter what. That's what we mean by over here. So over here we have how XA is pretty much how far the rope has been gone that way, and then YB is pretty much the distance away from the top, or how much rope is out from the top. And so we know that always has to be constant. Whatever is pulled here, this, no matter what, this stays constant. That never, ever changes. So we just kind of say avoid that. Pull this guy out. The more you pull this guy out, then you know that these three will respond. But since we know it's constant, you can see this equation. Every foot you pull out here, you'll only get 4 inches up because of this equation. And then you can take the derivatives of everything. We know that VA plus VB and A, and then this side's all 0 because that's constant. And so just equations pulled from the book to make sure, not the book, the PowerPoint, to make sure it's doing everything correct. Important to note, we're dealing with things in feet, even though we are given things in inches. So we want to make sure our units are correct. And so since we know the initial velocity of B, which means all three of these ropes are moving at the same rate, we can use this equation. sorry, make sure I'm using that correctly. Or, sorry, I should make sure I'm using my orders correctly. Sorry, we can use that to find the acceleration in a, I guess we could have done either order, potentially. But this equation to find the acceleration of b, actually, and we find out that this is just plug and chug. This is acceleration of b is equal to negative 6 feet per second. It would be important to note that this way is positive and that way is positive as well. So that means rope's going that way. And then our rope is accelerating that way. That gives us the acceleration of the weight, and then we can just plug into this equation over here. We get that A is equal to 18 feet per second squared. So how fast that rope is speeding up that way. And then velocity of A after half a second. We know that it is a constant acceleration, so it's just plug and chug into our equation here, and we get that is 9 feet per second. That is assuming that it starts with 0 velocity as well, and then assuming 0 velocity, 0 velocity, or initial velocity, which is 1/2 times the acceleration times the time, we get is traveled 2.25 feet. And then that was just for reference from before. I drew it the wrong way, so it didn't really make sense. But here we have a parachute, and it's initially free falling at initial velocity of 200 kilometers an hour. We'll change those units later. He opens his parachute at 600 meters. That's our initial position. And we know that he decelerates from 200 kilometers an hour to 50 kilometers an hour in a matter of from 600 meters to 586 meters. So we know it's 14 meters. And then it's constant rate of 50 kilometers an hour for a bit. And then we're also assuming that he does a constant deceleration as well at the end after 30 meters. And so we're just looking for the total time that it takes for after opening the parachute and what the initial deceleration is. So this is a thing where we actually end up finding part B first. Here's our graphs, just for visual. So we know this is not a straight line because the velocity is changing. So it's going faster, 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 and then at some point those meet up, go down, and then again he decelerates faster until velocity is equal to 0 there, and we know this is just constant. But here we can see velocity changing here, and the area under this curve is equal to the change in x. So we know that the area under this curve, because we're looking for T1 here, we have T1 also right there. That is going to be equal to that change in position, which is equal to 14, or negative 14, actually. And so we just take the area under the curve here, negative 13.9 times T1, and then you take the area of that triangle as well, which is shown right there. And we get that T1 is equal to 0.4032 seconds. Point that out over there too. The area under the curve is equal to the change in position. And then using that, we can use this equation, kinematic equation here. Oh, we know that is going. I Sorry, I totally missed that there. This is where we calculate what uh speeds everything is in meters per second. And just plug and chug into the kinematic equation. There's what we get, where we get our initial acceleration or deceleration. It's just going upwards. And then we're just using kinematic equations again. Just pretty much just plugging and chugging here. We know that delta x here, because there's no deceleration or not, it's just the velocity times time is how much that is going to change. We get that takes 40 seconds, or a little over 40 seconds, and then delta x3, which is going to be that area, or this whole area, is very, very similar. Um, Sorry, I should have written the equations that I was using down as well. But we get 4.32 seconds there, then total time, you just add them all up. Problem number 8, we're just looking for the three-dimensional motion, or we're looking to determine the magnitudes of the velocity and acceleration of the particle. Basically, this is just taking derivatives and then derivatives of the derivatives, and then just putting it all together. So this is our initial equation, that and that. And so what we do, we know that the velocity squared is equal to all its individual components squared as well. And so once we know that v is equal to dr over dt. We have t in there, so we can just take the derivative of that. You got to remember your sines, cosines, and chain rules, I guess. But yeah, after all that work, you end up over here, and just making sure you square everything correctly, and then you do the same thing, take the derivatives again, and did that up here. Square everything, multiply everything out, lots of cancellations. Making sure you know your trigonometry, making sure when things go to 1, when things go to 1, that simplifies a lot of things. And then you end up with its answers there. That is problem number 8. You can ignore this guy just to give myself space. And number 9, slow pitch softball has to be between 1.8 meters and 3.7 meters. We have an initial starting velocity and the angle that it's leaving. So we can break these up into 2 parts. The x and y components there. Initial velocity in the x direction, initial velocity in the y direction. Basically, we are looking for the maximum height, which is where you set the velocity of y equals 0, which will be somewhere up there, because at that point, if it's just the y, it's gone up, and it's going back down. I guess with initial height, it's gone up, then it's going back down. And we find that at 0.72 seconds, and then we can do a kinematic equation and find our initial y position, which was given, and then our initial y velocity, and just plug everything in. We find the max height is 3.16 meters, That is within the range, so we are okay. And then we have to find the time to reach the batter to find the height of the ball at the batter. So 2 steps. Again, we have max initial velocity. It starts at 0, so that just cancels out. We're assuming no deceleration or acceleration. So that's just time times the initial velocity, and we have the distance. So 1.39 seconds to get there. Height at the batter. Then you just plug in the t value again with all their other given values, and voila. So then problem number 10, we're looking for the initial velocity that would make it so that souvenirs can make it up to point B and not go higher than point C. So we're looking for a range, two-part problem. So we have to calculate the components out again. And we know that using this x, so we have initial 8 meters, and then whatever 10 cosine 35 is there. So we know how far it has to go. And then for y is 1.5 up plus whatever 10 sine 35 is there. So that's where we get those values. 16.19 is how far it has to go, and 7.24 is how high it has to be. And then the cool thing about this problem is that we don't know the initial velocity or how long it's going to take, but we know it starts at x of 0 or 0, so we can cancel that out. No deceleration. And so we know that the distance has to equal the initial velocity of x times t. And we know how far it has to go, and we know part of the angles. So we can get v of 0 times t by itself as an unknown to use later, and we can find that. Actually, that would just be meters. That's my bad. Then we can do a similar thing for y as well. But where am I going here? Yeah, so just plug things into equations. Oh, we know y0 is equal to 2. We don't know that yet, but we have, remember, we have the v of 0 times t component part from there. We can calculate sine 40, that's very easy. And then we don't know t quite yet, but that's what we can use this for, is that we can get t squared on its own and then do a little algebra and find that it takes 1.3 seconds to get there. And then since we know t now, we can solo out v of 0, which you can see right there, and then 16.19 divided by 1.3 times 1.3 cosine 40. We get the initial velocity to reach point B is at least 16.2 meters per second. And then we do the exact same thing for C. So I think I went through the exact same process, finding the values we have to get to, height and distance, and then literally the exact same process. This is the exact same thing as there, just a little bit different numbers, and we need a fire between 16.2 meters per second and 20.96 meters per second. That is that problem there, just to give space. This is a very simple problem. It's all about centrifugal acceleration, or the normal tangent path. So spinning around in a circle, that's kind of a tangent. It's kind of like you're always going away, and then this is what you're being kept from going out. So you're being drawn in, I guess. And then, so we are not accelerating in the tangent direction whatsoever, so we can kind of ignore that and see that goes to 0. And then, so we know that the acceleration is all equal to this. This is velocity. This is the instantaneous radius of curvature. And we know that we're trying to pull 3 Gs. So, and then we're looking for the velocity that they're going with the 5-meter radius to experience 3 Gs. A little bit of algebra, we get v equals 12.1 meters per second. A very similar problem again. No constant speed, so tangent acceleration is equal to 0. Then we know we have a velocity, and we're looking for a radius this time, so a little different. 4 Gs is equal to v squared over the radius. Yeah, a little bit of algebra. We find the radius that the plane can handle is 1,467.9 meters. That's the minimum radius that it can handle. This is probably the hardest problem conceptually that I struggled with. It took me a bit. We start off with a conversion rate. 315 miles an hour is equal to 462 feet per second. I threw a lot of things out. Yeah, lots of screenshots from the book of equations to help understand and justify myself. But here we have R. We are looking for how fast this R is changing, or this is velocity R, so kind of how fast it's going. Like if it only goes up to here, then how much if it goes up to there, and such. A little confusing. But then we also know how to visualize it. Using velocity, we know that it has to add up to 462 feet per second there. I guess Pythagorean theorem up to that. And so we also can calculate this angle omega by using, we have a 3, 4, 5 triangles, so that's equal to 3,000 as I put it here. You get that angle also. And then, so can use, find the velocity of r using, just trigonometry. V of r is 369.6, and then the omega is negative 277.2 because it's going down. And it doesn't really matter if it's up or down because, I guess it, when it squares it, or when you square it, it makes it positive. And so from the book, or I guess there's more set up here as well. So you would be able to line this up with R. This is ER. This is our same omega is right there. And then this is E omega, or it's a vector as well. And so from the velocity here, we know that this is a given equation. And so from this and that from the book, we know that v of r is equal to r dot. Remember, that's r, derivative of r with respect to time. And we know that v omega is equal to r times omega dot. So we know that VR is, we already have VR, so we know r dot is equal to 369.6 feet per second. And then we have the radius and we have the omega, so we can find omega dot very easy, which is negative 0.0924 radians per second, which I believe that means how fast that is instantaneously closing at that point. And this means how fast this radius is going up, or it's like getting away from at that point or expanding. I may be wrong, but I will see, I guess. And then this is where it probably got confusing. Just set up going through pretty much had to go through the textbook a bunch for this guy just to kind of look. Obviously, I mean you can see all the different equations, obviously. And so uh, I finally had the epiphany. So we know, sorry, it's important to set up A of t tangent is accelerating in this problem as well, and we have a constant horizontal velocity at the moment, but of course it's going up. So this is the plane's tangent acceleration, and then this is the normal force of the plane as well that is driving it up. And so we know that the acceleration of everything must be the same because it's based on each other. So we have A and we have A. And so we can set this up here. And actually, well, we can set this up here. We have this is dv over dt, which is equal to A tangent. You can see that here. And A normal is equal to that. We were just going over problems with that. And so we know that all of these components have to add up to the same acceleration. And we can break these down, even though we already know the angles between them, because that's ER, E omega, and such. But we know that AT and AN must add up to ER and E omega. So break it down here. And such, and so, so sorry, A tangent is given, we have to calculate the A normal, but we have the velocity, and we are on a 1 mile radius, so it's 5,280 feet. And then calculating this is still still A omega, AR, and so that is where, oh yes, sorry. So those are A omega and AR, and so A omega is this guy over there, and we know that is the AN cosine theta and AT sine theta, but as you'll see, it can only go in one direction, and this goes that direction, and this is not to scale whatsoever, but then you also have that that's going the other way, so that's subtracting, and so we do that, and we already have all of these values, so plug and chug, we get A omega is equal to 26.34 feet per second squared. AR then is AT cosine theta, which is that guy. We're going this way and this way, so they're both going that way for the AR components, so they add up. Again, have the value, so we plug and chug, and we get 32.255 feet per second squared. And then from textbook and other equations as well, or lectures, we have given equations. So the AR is equal to R double dot minus R omega dot squared. And so we have all of these values, so again we can plug in, find R double dot, and then again we have this A omega is equal to R double dot plus 2 R dot omega dot. So again, we can plug everything in because we have everything, and we get omega double dot is equal to 0.032 radians per second squared, which I believe that means that it's starting to open up, or after this it's going to start to open up. I don't know. I'm still trying to understand that one conceptually. Then for the last problem, we have number 14. Very similar problem to before, except different starting conditions, and we have two weights, and they have a different number. Weight A has 3 ropes on it. Rope B has 4, so that will change how they operate. Same thing though. Rope length is constant. You can show that here. That means you can take the derivatives, get the velocities, it's equal to 0. That doesn't change. Total. And then we have the accelerations as well, again, equal to 0. And so we have to do a little bit of thinking here. And so we know block A always moves with a constant acceleration, and block C also moves with a constant acceleration. And if you look over here, if these all equal a constant value, that means that block B also has to move with a constant acceleration, which I put right there. All three have to add up to 0. And so we aren't given block A's acceleration, but we do have the velocity of B after 2 seconds, so we can find it. These kinematic equations are for constant acceleration. So eventually we get AB is equal to 244 millimeters per second squared. Again, I need to put which way is positive, because that would very much so help when we're defining things, but it's always good to specify. And then we can put since we know the initial acceleration, or the constant acceleration of B, and then also B and C, we can find the constant acceleration of A, which is 345 millimeters per second squared, going up. This B's going down, and this guy is going that way. It's weird to look at, but I mean, I see it. You pull up, this guy's going down, and then this guy's going up. So somehow the ropes make it happen. But since this guy has 4 ropes and that guy's 3, it works out somehow. And for part B, we're looking for the initial velocities of A and C. We know that block B starts from rest. So we know we're taking everything from 0. Oh gosh, hold on. No, because we know, looking using this equation here, we can find the initial velocity of C. We know the acceleration, and I believe we do know the time. And we know the final velocity, so that gives us the chance to find the initial velocity, which is 130 millimeters per second to the right. And then that allows us to help find A, because we know initial velocity of B is 0. That we know it's 130 plus 3 times the initial velocity of A. It's 3 because of the number of ropes. Just remember that. And then we know that the initial velocity of A is negative 43.3 millimeters per second, which means it is moving that way initially. And then part C is just the change in position of the slider block C after 3 seconds. So assuming it starts at, say it starts at 0, as we're just looking for the change. We have the initial velocity, we know how long it's going, and we have the acceleration. This is easy, it's just plug in and we get 727.5 millimeters to the right. So it means it starts here and goes over there, 727.5.